Hi everybody, this is Jim Corkins, and we're continuing on with the second part, well actually the third part of the rotation module, which is about rotational inertia. Okay. So again, if you haven't done the reading, please read the OpenStax textbook or Survey, should you have those, or the if you're in Physics 101 and 111. If you're in Physics 121, please read OpenStax or the Knight textbook. And if you're in any of those classes, please read Coletta chapters 9 and 10. Okay, so what is rotational inertia? Well, rotational inertia is basically the same concept as what Newton introduced back in forces of what inertia is. And essentially, inertia is just mass. Okay, so rotational inertia is analogous to mass. And for example, back in forces, Newton's first law is an object in motion will tend to stay in motion moving in a straight line unless acted upon by an outside force. Well, the same concept kind of goes for rotational stuff. Rotational inertia is when an object is rotating about an axis, it'll remain rotating until acted upon by an outside force. Okay. So rotation, a rotational inertia is essentially the same concept of mass, but just going about a circle. Okay, but that actually, since it's analogous to mass, if a mass is moving at you with a high rate of speed, if a small mass is moving at you with a normal velocity, it would be relatively easy to bring it to a stop. But if that mass was 100 times its mass, it might be more difficult. So mass inertia is a concept of a mass resisting its state of motion based on its mass. Well, the same concept goes for rotational inertia. Higher rotational inertia, which is considered to be analogous to a higher mass, is going to have a harder time to change its state of motion. Okay, so you could test this by using your pencil. Okay, so here you have a pencil, and if you're just spinning your pencil around the center of it right here, just rotating it around here, you'll notice that there is, let me do this. I'm going to do something. I'm going to mark this up. Okay. So notice here along this central axis, right here, here's the center axis. It's along this line right here. Okay. A lot of the mass is really close to the central axis, right? So the mass of all these pencils are all the same, but here the mass is, well, actually, let me write the moment of inertia for something, just the basic formula for a moment of inertia. That r squared is important, okay? Because if a lot of the mass is close, its distance from the central axis, which is what r is low, then that is going to make the moment of inertia really low by the square of that number, right? With the next part, so if you're spinning this one, it's really easy to spin and change it. So just like wiggle your pencil around here. So you'll notice that's kind of really easy to change. Once you try to wiggle your pencil this way, where it's spinning around this axis right here, you'll kind of notice that it's a little bit more difficult to wiggle it, right? There's a little bit more resistance, okay? And that is because the mass here, a lot of the mass is really far away. So this R right here is I don't know, 10 times this R. If this is just 1 R away from the central axis from here to here, let's call this something like 10R. Okay, so well now, and this isn't the formula for this, specific one. The actual formula for the moment of inertia is actually 1/12 mr squared, but we're just going to be consistent with our equation up there. So the moment of inertia, if just to stick with the concepts of this, so it's got the same mass, but its r is 10 times the r there. So this is actually going to be 10r squared, which is going to be 100 times more difficult. It's going to have 100 times the moment of inertia. So it's going to be really, really difficult to spin this compared to this one. And I know it's just a pencil, but if it was a more massive object, this would be significant, right? Because mass is analogous to the moment of inertia too. Okay. All right. Well, now if we look at this final one way down here, if you try to spin your pencil and just wiggle it about one of its ends, like right here, you'll notice that this distance here, if this is 10r for half of it, we'll call this distance, I don't know, like 20r? Because, yeah, that totally makes sense. Okay, so that's 20r to right here. So anyways, so this moment of inertia, conceptually, well, the actual moment of inertia for this, by the way, is just, I think it's 1/3 mr squared. But we're just going with an analogy to the equation right here. This moment of inertia is going to be 20 times the radius, so that's squared. So that's going to be, what, 400 mr squared. So this moment of inertia for this object is going to just be, 4 times the second one's, right? So it's a lot more difficult to spin. And this is 400 times more difficult to change its motion than the very first one there. If this is like 10, if this is like 1 millimeter and this is 10 millimeters, you know. So my point is, it drastically increases based on that distance. Okay. All right. So this is kind of an analogy, and this is the concept of moment of inertia as analogous to mass, but it's a mass rotating about a circle. Okay. Well, we're going to find out later on using torque, which is a force about a circle, and we'll get to that when we get into torque, that torque, when you sum up all of your torques, like you sum your forces in the x direction, you sum your forces in the y direction, well, now you'll have to sum your torques, where you're going to set that equal to the moment of inertia times an alpha. This is analogous to force is equal to mass times acceleration. So this is the rotational form of forces. Okay. And so when you apply a force about a circle, that's called torque, right? And I'm going to rewrite the equation so that we have a nice analogy here. So when you're wiggling something, when you're wiggling your pencil, and that I'm just assuming that you're providing the same torque or constant torque to each one of those earlier objects when you're wiggling your pencils about different centers. The reason why it was hard to change its motion is because, well, the moment of inertia is inversely proportional to acceleration, right? Just like mass, it's harder for this. Force over mass is equal to acceleration. A larger mass is going to have a lower acceleration. Well, the same kind of concept is going with here. A larger moment of inertia is going to have a harder time changing its current state of motion. Okay, so that's how moment of inertia is interchangeable with mass, is conceptual wise, and that's how moment of inertia is related to this concept of changing acceleration to. Later on, we're going to get into how to find rotational inertia and integrate it for different shaped objects, right? But in the end, you can add up the moment of inertias for different objects, right? So the moment of inertia for a point mass is just the mass times, is that point mass times its distance to the pivot point or the rotational axis, right? Well, in this object right here, essentially you have mass 1, mass 2, and mass 3. So you could sum up the total moment of inertia about this object by calling it the sum of mass 1 and times R1 squared plus mass 2 times its distance squared plus mass 3 times its distance squared. So anyways, if all of these are the same mass and they have the same distance to the center, then what you could say is that this is going to be 3mr squared for the total moment of inertia for this object, right? So, and that's basically the concept that's leading into this. Except the weird part when we get into that integration is you're integrating a function of describing the distribution or the density of masses from the center point, right? So there could be situations where you have a homogeneous rod right here. Let's say this rod is spinning about this axis, just kind of like you were spinning your pencil about one of its ends, right? So this would be a nice linear mass, right? Lambda, right? And that would be the length, and let's say the mass is evenly distributed across this. So this chunk right here, let's just take chunks. This chunk's of mass is equal to this chunk of mass is equal to this chunk of mass. And so all those masses are equally distributed incrementally, okay? So there's a density kind of situation here. And it's the mass per unit length, and that would go into this. But we'll get into the specifics of that later on. But essentially, that is leading into this description of the masses distributed about this center point, and then you're going to integrate this, and you'll end up getting like your L will cancel out with this, so each of these masses, so this is going to be a distance to this, and this distance to this point, this distance to this point. So you're going to have to equally, you're going to have to account for each one of those distances in this one equation right here, which is the density distribution over this. So it's really kind of fun. And we'll talk about that when we get into the calculation of center of mass in the next part. But for Physics 111 and Physics 101, essentially, it's just you're going to find for a point mass and its distance, and then you'll just add those up, and it's going to be a pretty easy calculation. Speaking of this, there's an alternate. Every now and then you're going to be given an object, right? And this object has a moment of inertia of 2/5 mr squared, where r is the distance. From the spinning point to the very outer edge of this, right? And so when you integrate this sphere, by this integral right here, you end up getting a moment of inertia that is 2/5 mr squared. Okay. So this is considered a sphere, a solid sphere, spinning about a circle, kind of like a bowling ball. Okay, and so when you integrate that, you end up getting 2/5 mr squared. So if you're in Physics 111, you're not going to have to integrate that. You could just memorize this, or just it could be given to you on a test or something like that. But This is the moment of inertia for the center of mass of this object. Well, what happens if you're not spinning this object around the center of mass? What happens if you choose to spin it around it over here at an axis a distance d away? Okay, so what happens if you do that? Well, when you do that and you choose to spin it around another part of this object other than the center, you have to use the parallel axis theorem to figure this out. So here what we're going to do is to find the total moment of inertia is you take, to apply the, if you're spinning it around this center over here, what you have to do is take the center of mass moment of inertia, which in this case is the solid sphere's 1, mr squared, and then what you're going to do is you're going to add that total mass again and its distance and treat it as like a particle or a point mass. And in this case, d is the distance from distance d here in this equation is distance from the center of mass to the rotational axis. So that's mr squared. So I'm going to factor out mr squared here, and then you get 2/5 plus 1. And so that ends up being 5/5 and added to 2/5. So that equals mr squared 7/5, or in other words, 7/5 mr squared. So that's so every now and then they might give you might be given a problem where you are given a solid sphere, but you're not spinning it about the center of mass. You're spinning it about one of its edges. Well, in that case, you're going to have to apply the parallel axis theorem to do it. And as you can see, it's not too difficult. You just need the equation for the moment of inertia for whatever object, and then you'll apply the parallel axis theorem, which is just the mass of that object times the distance from the center of mass of that object to the pivot point, and then go from there. So a lot of different objects, you're going to be dealing mostly with objects that are like a rod being spun about its center of mass, a rod being spun about one of its edges, a hula hoop or a hollow cylinder or a solid cylinder, a solid sphere just like we just did with the bowling ball, or a hollow spherical shell kind of like a basketball, right? And all of these objects have their own different moments of inertia based on their integrals and distribution of mass. We're assuming this is a homogeneous distribution of mass for all these integrals, right? So you notice, if you look at this equation and I were to ask you, why don't you assume all of these distances, assume L is equal to R, and all of these masses are equal. I'm not worried about the central plates or anything, but I want you to arrange the moments of inertia for all these different objects from highest moment of inertia to lowest moment of inertia, assuming M is equal to R. So please go ahead and try that. Pause the video now. Okay, well, if you've done that, then the one with the largest moment of inertia, which is actually the same thing as a particle, by the way, is just let's say this is the axis and you're swinging a ball on a rope or something. This is the particle. This is mr squared, right? Well, it turns out that a hollow cylinder is actually the same moment of inertia as a particle, right? So the moment of inertia for a hollow cylinder in these problems is going to be the largest one, mr squared. And that's going to be greater than the next one, right? The next one, it looks like 2/3. It looks like the hollow spherical shell has the next largest moment of inertia, right? Because this is 1 mr squared and this is 2/3 mr squared. Now it looks like the solid cylinder. The solid cylinder is going to be 1/2 mr squared. And then it looks like 2/5 mr squared comes next, which is the solid sphere. It's 40%. And then the thin rod about the end, which is 1/3 mr squared. And then finally the thin rod about the center, which is 1/12 mr squared. And I should say L squared for these guys, but L is equal to R. Anyways, so you're going to be doing problems primarily with either just a single particle spinning about the center axis, or a hollow cylinder, or a solid cylinder, and comparing those with these other objects like the solid sphere, the hollow sphere, the thin rod about the end, the thin rod about the center. So get familiar with these equations. And the best way to do that is just to rank them from largest to smallest moments of inertia. Right? Okay. All right. So we've got this object, and here's the next problem. We have a uniform thin rod of mass m, which is 4.41 kilograms. It's going to be pivoting about this center through an axis through the total length of the rod L. So the total length of the rod is L. And it says you have two small bodies of small m, and m on its center. So that means if the center is here, that the green m is L over 2, and the kind of orangey m is L over 2 away from the center. So the total length m, total length L. They're attached at the ends. What must the length of the rod be to find the moment of inertia for the three-body system? This m, the rod, and the green m, three bodies, with respect to the described axis right here. And they're basically saying the total moment of inertia here, which is the sum of the moment of inertia for the whole system, is 0.957. And so we're going to find out that this length is going to end up being 1.22 meters. Well, what we learned earlier is that you could sum up all of the moments of inertia. Okay, and it was earlier, I mean this part, right? You just sum up all the little moments of inertia and just total it. Okay, well, we're going to do that right now. So what we have is we have a point mass a distance away, and that is mr squared. We have another point mass a distance away, and that is another mr squared. And we also have a rod spinning through its center, which is 1/12 ml squared. So we're going to total the rod's moment of inertia plus one of the small masses moment of inertia plus the other small masses moment of inertia. Okay, and these two moments of inertia are going to be the same. So essentially, the rod's moment of inertia plus two of those small masses moments of inertia. Okay, that is going to be equal to, the rod is 1/12 m, and this is capital M. Got to distinguish it. These are small m's. L squared plus 2 times the moment of inertia for the single mass, which is small m. And I'm getting close to, comfortably close to this right here. I'm going to move that out of the way for right now. That's going to be equal to 2 of those. It's 2 of those small masses. So I'm going to times that by just m, and their distance from here, which we said is r squared. Well, that r is the distance from the mass to the pivot point, and that's going to be L over 2 away from the pivot point squared. So that's L over 2 squared. I'm just going to do that big kind of bracket to distinguish those brackets. Okay. So the total moment of inertia, which is 0.957, is going to be equal to 1/12 capital M L squared. And I got to make sure that looks like a small m. Small m. That's small m. So that's 2 of those. So this is going to be equal to 2m. And that's L squared over 2 squared. So that's L squared over 4. Okay. Well, that 2 is going to cancel out with that 4 to become 2. So this is going to end up being 1/12 capital M L squared plus looks like this is just going to be 1/2 small m L squared. Okay. All right, here we go. Let's pull out some variables, right? Let's do this. I'm going to pull out an L squared, and I get 1/12 capital M plus 1/2 lowercase m. All right. And that is going to be equal to our moment of inertia. Well, what essentially this is saying is the total moment of inertia is equal to L squared times 1/12 capital M squared, capital M plus 1/2 lowercase m. Right? You can divide both sides by that total. So the total moment of inertia divided by 1/12 capital M plus 1/2 lower m, that's going to be equal to L squared. Where then if I just square root both sides, then I get this. Then I get this as our total here. Okay. All right. Let's start putting in some numbers. All right. So that means we got a square root, and this is the total moment of inertia is 0.957 kilograms meters squared. And that's going to be divided by 1/12 of the big mass, which was 4.41 kilograms. That's the mass of the rod, plus 1/2 the mass of the small mass, which is going to be 0.553 kilograms. Okay. All right, let's see how this works out. Hopefully it's going to add up to 1.22. So that's going to be 0.957 divided by parentheses 4.41 divided by 12. Actually, I'm going to put 2 parentheses. 4.41 divided by 12 in that parentheses. Add that to 0.553 divided by 2 divided by 2 end parentheses equals. And then we're going to take the square root of that. And that works out to be 0.219, or, I mean, 1.219 or 1.22 meters. Very cool. So the lesson will be learned here is that what do you do if you have to find the total moment of inertia for several objects about a center? Is you note their distance to their center. So both of these little masses are distance L/2 away from the center pivot point. But they're on a rod, so you have to account for that rod too. So what we did is we added up each one of those moments of inertia. the moment of inertia for the rod, plus the moment of inertia for one of those little masses, plus the moment of inertia for the other mass, which are the same. So we then just said 2 times that to simplify it a little bit. And then we put in our moments of inertia. Did some algebra and try to refine this down to be something kind of simple to easy to work with. And then solve for L, and then put in our numbers, and that's what we did. So basically sum up all the moments of inertia to get the total moment of inertia of the system. Okay. So this next problem is a really fun problem. Essentially, you're doing the same thing as the last problem, but now you're just concentrating on the rods. Okay. So what they're saying is that each one of these rods, and they colored them too to make it easier for us to figure that out, is a length 0.675 meters. So the total length is 0.675 meters. And each mass is equal to each other. So they all have a mass of 2.91 kilograms. Okay. So the trick here is, first of all, knowing the moment of inertia for a rod is 1/12 mL squared. But if it's for a rod about the center, but then you also have to know the moment of inertia for the rod being spun about its one of its ends, which is 1/3 mL squared. So we're going to be dealing with either 1/12 mL squared if it's about the center, or 1/3 mL squared if it's about one of its ends. Okay, C and E. All right. So let's do this first one, A. What we have is, it looks like we have 1, 2, 3, 4 rods. So the total moment of inertia at A is going to be this red rod plus this orange rod plus the blue rod plus the green rod. So that's 1, 2, 3, 4 rods, 4 moments of inertia being spun about their center, which is going to be 1/12 mL squared. I'm going to reduce this down just a little bit, make it easier to put in my calculator. So that'll end up being 1/3 mL squared. It has nothing to do with this one, so don't confuse those two. It's just, this is a product of, this 1/3 is from reducing 4 divided by 12. And let's see if we could go ahead and put in some numbers to see if we find out what the total moment of inertia at A is. Well, what we'll have is the mass is, well, the length is 0.675 that we're squaring, times a mass, which is 2.91 kilograms. Okay, and divide that by 3. 0.4419, or 0.442. 2 kilograms meters squared, which is units of moment of inertia. All right, cool, very cool. Basically, this one is 4 moments of inertia. This is the center, and this is ends being spun about the center of the rod. And that was the total at A. All right, this next one adds a layer to it, if you could say. This one, it looks like this is a rod being spun, the green rod is being spun about the end, while the red rod is being spun about the center. So the sum at B, sum of the moment of inertia at B, is 1 center rod plus 1, which that center rod is that brick colored one, and 1 end rod being spun. So that's going to end up becoming 1/12 mL squared plus 1/3 mL squared. We could probably reduce this by pulling out mL squared, and now we got 1/12 plus 1/3. 1/12 plus 1/3, what is that? That's 4 divided by 4, so that's 5/12. So this is going to be 5/12 ml squared, which is the total moment of inertia at B. And now we're going to plug in our numbers. Well, again, it's just 0.675 squared times the mass, which is 2.91 equals, so that's 1.3258 times 5 equals divided by 12. 0.552 kilograms, 0.552 kilograms meters squared. Let's try writing it with numbers that we could read. 552 kilograms meters squared. Cool. Cool. Let's try the next one. Well, this next one is kind of interesting. It looks like it's one rod, okay, that is twice the distance. So we could actually make this problem a little bit easier. And not, so this looks like it's going to be two rods, two L's away. And this is a mass M, and this is a mass M, so the total mass is going to be 2m, right? So the sum of the moments of inertia at C is going to be, it's going to look like it's one rod spun about the end, which is 1/3 ml squared. But this is a rod, these are two rods stuck together, so that it's got twice the mass, but it's also got twice the length squared. So that's 2L squared. So this is going to work out to be, we're going to reduce this down as much as we can. So this is 2m, and this is 4L squared. So this is going to end up becoming 2m times 4L squared divided by 3, which is, what is that, 8 divided by 3? Was that 8/3 ml squared, which is the moment of inertia at C. So the total moment of inertia at C is going to be 8/3 of this total, right? This is now a total distance 2L, and it's 2 m's. So that is going to be 0.675 squared times 2.91 equals times 8 equals divided by 3 equals 3.54. So this is going to be 3.54 kilograms meters squared. Okay. The last one is really neat, and we're going to have to get creative again with this one. It looks like you've got this brick-colored rod right here, which is spun about its end. So that's going to just be 1/3 ml squared. But this rod right here looks like it's going to be also a rod spun about its end, because I'm going to say this is just one rod spun about its end, and this is just another part of the rod spun about its end. But this one is 1/3. It's a rod spun about its end, but this guy is an M over 2. It's a half mass, and it's also a half length, and it's L over 2 squared, right? Because it's half of a rod, half of a full rod, so we got to take the mass divided by 2 and also the length divided by 2. Well, this guy right here, so hopefully that makes sense. This next one is a full rod plus a half rod spun about the end. So that's 1/3. And that's a full rod plus a half rod. So it's got 3 halves a mass, but it's also got 3 halves a length that we're going to square. That's 3 halves L squared. Clean that up a little bit. This is just supposed to be an L. I don't know what happened there. It's 3 halves L squared. So this is probably, it looks not as complicated as this one, certainly, but it actually turns out to be quite complicated, I think. So let's start off with the brick one. That's just 1/3 ML squared. And let's do the next one. That's 1/3 M over 2 times L over 2 squared. And let's try to add in our last one, which is 1/3. Whoops, I'm going to run out of room. And it's going to be plus 1/3. So all this plus this, which is 1/3, 3 halves M times 3L over 2 squared. All right, well, I'm going to try to give myself enough room. So sum of the moment of inertia at D is going to be equal to 1/3 ML squared. I'm going to multiply this out. L squared over 4, L squared over 4, L squared over 2 squared is L over 4, times M over 2, so that's going to be plus 1/3, and that looks like it's going to be ML squared over 8. So this is going to be 1/24. I'll do that in the next line. So L squared over 2 squared is 4, and 4 times 2 is 8. So that's ML squared over 8. And I just left the 1/3 there. This is going to be 1/3, and this is going to be 9L squared times 3. What's 9 times 3? What is that, 27? I should know that. Yeah, 27. I always doubt myself. So this is going to be 27 ML squared on the top, and it's going to be 8 on the bottom. All right. So this total moment of inertia at D, I'm just going to write out 1/3 ML squared plus this is ML squared over 24. Actually, I'm going to put this in a same format. ML squared over, this is 1/3 ML squared, which is just ML squared divided by 3. This is ML squared divided by 24, 8 times 3. And this is going to be 27/24 ML squared. Phew! All right. Just to make it a little bit easier to do the math, I'm just going to pull out an ML squared out of that and just do 1/3 plus 1/24 plus 27 over 24. And I'll just do that separately. So the moment of inertia at D, when I do all that, let's find out what that's going to be equal to. 0.675, and I'm squaring that, times 2.91 equals, I'm going to then multiply that times 1/3 divided by 3 plus 1 divided by 24 in parentheses plus 27 divided by 24 in parentheses equals 1.9888. So that's 1.99 kilograms meters squared. Pretty cool. Well, in the next section, what we're going to do is we're going to go through how to calculate center of mass, and then we're going to use that using integration, and then we're going to also calculate, we're also going to talk about calculating center of gravity and how they're different and the same, center of mass and center of gravity. But also we're going to go through how to calculate and integrate moment of inertia for different shaped objects. Okay, that'll be in the next section. I hope you had fun. Thank you.